Okay, so this is super easy. I'm just taking the integral of 10 square root of 425 30. And
T cubed.
from 0 to 1 t cubed dt. And in the end, I have what I have. So it's going to be 10 square root of 30 t4 divided by 4 from 0 to 4. So I have 1 over 4. So it's going to be 5 square root of 30 divided by 2. Okay? So this is going to be the number in the line integral. And if you're interested in what this number represents, I give you not a very mathematical explanation. This is sort of like the weighted R class of the line. Weighted R class of the line. But we will be able to see the full power of this line integral once we talk about this conservative vector fields and the fundamental theory of calculus. Okay? So this is pretty much all the things we can talk about line integrals with respect to a scalar function. I also, I'm sorry.
Why is the range from 0 to 1?
Oh, this is the initial point.
Mm-hmm.
Right?
Yeah.
Which means the initial time should correspond to this point. So when I look at this formula, which number I plug in for t will give me this initial point? 0 is the one. So that's why I figure out 0 is the initial time.
Mm-hmm.
And this is the terminal point, which means I need to figure out what value of t I plug in this formula, I will get this point.
Okay, and when
Right.
you plug in 1, it's
1, I get a
1 to 5.
1 to 5. That's why I figure out these 2 points.
Okay.
Yeah, that's a very variable question. People have to definitely understand what's going on here. Yeah, right.
I think you messed up and put
Oh,
it 4.
divided by 2.
It's
Divided by 4, so it's going to be 5. Oh, no.
No, I'm talking on your range right next to.
Oh,
T.
0 to 1. Yeah, exactly. 0 to 1. The answer is still correct.
Yeah.
Any other questions? Yep.
How do you get the square root of 1 squared plus 2 squared plus 5 squared?
Okay, yeah, this is another very variable question here. So this R prime, I'm going to put it here, which is pretty. The length of R prime is the arc length element. This guy, by definition, is equal to x prime t squared plus y prime t squared plus z prime t squared. Know what I mean? So this is x prime squared plus y prime squared plus z prime squared. And by the parametric equation, I find x is equal to t, y is equal to 2t, z is equal to 5t. So when I compute the x prime t squared, I'm getting a 1 as the derivative square, and this is 2 as the derivative with respect to t of y, and this is where I get 5. Okay, so in this particular example, it is equal to t prime squared plus 2t as a prime the square, then plus 5t taking the prime then square. Okay, and that's why I have 1, 2, 5. Okay. Any other questions? Okay, next, we're going to talk about a slightly different line integral. Okay, so now I'm still looking at a curve. Okay, I'm still looking at a curve defined by a parametric gradient RT. Okay, I'm still looking at a curve. Let's see, we're on R3. So instead of taking the line integral with respect to a scalar function small f, I want to take the line integral of the vector field. But here I have to be very careful. So if I have a vector field, it's given by F, G, and H. Okay? So for any given curve, as long as I have the parametric equation, I can always compute the R prime, the first order derivative. And we actually learned about this r prime to the 4. This first order derivative is nothing but the tangent vector. Have we talked about this before? It's last semester in G50. I did talk about the tangent vector here. But this semester probably the limit the material. So this r prime, the first order derivative. For instance, if I have a curve given by r t, at any given point, if I want to find the tangent vector,
yes,
I find the first order derivative.
Yeah.
Am I right?
Okay.
Did we talk about this?
No, it's makes sense.
Right? But we're talking about everything now, so it doesn't really matter here. So
Okay.
if I have a vector function to define a curve, if I want to find the tangent vector, I'm taking the first order derivative. Okay?
Yeah.
I'm taking the first order derivative. This is nothing but a tangent vector. Okay? I'm taking the tangent vector. So if I want to take the line integral, I want to get a number in the end. At every given point, I have a tangent vector given by the first order derivative. Okay? I also have a vector given by the vector field. Okay, listen to me carefully. I also have a vector given by the tangent, given by the vector field. These two vectors are very likely different. Right? They can be completely independent of each other. You know what I'm saying? One is determined by the curve. The other one is determined by this vector field. Okay? So if I want to take an integral of this vector field along this line, and in the end, I want to have a number, I have to be able to get a number coming from these two vectors. And that's the only chance I can get a number which is taking the dot product. Okay? So in order to take the integral of a vector field along a line and get a number in the end, this is the only way you can do it. You have to take the inner product of the vector field and the tangent vector, which is given by the first order derivative. And you get a number here, you take the integral in the end, this is going to be defined as the line integral of a vector field along a curve. So this is the only way we can define a line integral to get a number. There are other ways to take the integral to get a vector. But this is the only way you can get a number in the end. And this number is particularly interesting. I give you one example. Okay? I give you one example. Imagine if along this curve there's a train or any automobile, and you want to drag this train or automobile along this curve. By dragging, you have to put a force on this train. A force consists of the magnetic field, which is how hard you pull, and also which direction you're pulling. All right? So if this vector field is talking about the force you're putting on the train, and you're dragging this train along a curve, you take this line integral, you're going to get the total work you've done along the curve. Okay? You're going to get the total work of the dragging along the curve. I give you two very easy examples of this. For instance, if I move the train along the curve, and at every single point on the curve, I'm dragging the train in the orthogonal direction of the curve. You're dragging this as hard as you can, but you're not doing any work. And that is reflected in the dot product here. If two vectors are orthogonal, taking the dot product will give you 0. So you take the integral along the curve, as long as you keep orthogonal everywhere you pull, in the end, even though you're pulling pretty hard, but you're not getting any work done. Okay? In other words, imagine if you're pulling a train along the curve and you want to get your work done as efficiently as possible, which direction will you pull? You have to pull in the same direction as the tangent at every single point. And that is also reflected in the formula. If I want to maximize the dot product, I have to make sure these two are parallel, or these two are pointing to the same direction. Okay? So this is why we have a force dot product with the tangent. This is exactly talking about the work you can put on dragging a force, putting a force on a train or any other moving object. Okay? And this is also an extremely popular problem they will throw at you for line integrals, which is this work done by a force. Okay? So this is the general formula, but overall we have the formula that from CF dot to DS going to equal to the integral from a to b. So let's say my curve is going from t equals a to t equals b. So I'm taking the integral of the dot product between f, t, and h. Dot product with r prime, which is x prime t, y prime t, and z prime dt. Okay? So this evaluation of the line integral of a vector field along a line is going to be equal to the dot product between this guy is equal to my capital F. This guy is equal to the tangent, which is the r prime of t. Okay? So if you take the first order derivative of a vector function here, you're taking the first order derivative to each component, right? So x prime, y prime, right? And then you're doing the inner product. So in the end, I'm doing the inner product of these three vectors. Essentially, it's going to be f times x prime of t plus t times y prime of t plus h times z prime of t. And I get a function here, and then I take the integral with respect to t. Okay? This will be the integral we need to evaluate. So in the end, as long as you understand what this formula is, okay, I have to take the derivative here. The key part of doing any line integral is to figure out what the parametric equation is. All right? The key part for every line integral, if they already give you the parametric equation, everything is pretty nice. You just plug in what is needed. If in most of the cases they don't give you the parametric equation, the key part is to figure out what the parametric equation is. By parametric equation, not only you have to figure out the three formulas, but also you have to determine initial time and the terminal time. That's what we did here. Okay. So let's begin from the easiest case, where I give you a parametric equation already. So let's see if I have a curve which is given by rt is equal to 8t 3t squared. By the way, I'm writing these formulas in 3D, but the same formula, the similar formula will work in 2D as well. You don't need to contain this z component for each component, but you're still doing the inner product. You know what I mean? So I'm writing it in R3, but an extremely similar formula will be valid on R2. So this is the curve in R2, where I know t goes from 0 to 1. And the function f is a pretty easy real function x1. So I want to compute c f dot t dx. Okay. This is what we have. Okay. We already have the parametric equation of the curve. So the only thing we have to do is to plug in everything. Okay? The only thing we have to do is to plug in everything. And I do want to ask you a small question here. What is this curve? X is equal to 18, y is equal to 3t squared. It's definitely not a line anymore. All right? This is definitely not a line anymore. This is a parabola. I already heard the correct answer, but also because we're so used to seeing x and y, right? So if we have an equation where y is equal to whatever of x, then we immediately know what it is. So if you're not sure about what this parametric equation defines, you can eliminate the variable. Am I right? By solving these two equations, x is equal to 18, y is equal to 3t squared. And the elimination is pretty easy here. First equation gives you t is equal to x divided by 8, and then you plug in the second equation. All right? So you can simply do the substitution to eliminate t, so y is equal to 3 divided by 64 x squared. This one seems much more friendly, right? And it is a parabola opening upwards with vertex 0, 0, right? Are you with me? Mm-hmm. But I do want to make the following remark. Calculus is independent of graphing or imagination. Right? It is independent. If you have very good graphing skill, If you have very good imagining skill, it will help you tremendously. But you can still do pretty well in calculus without any of this skill. For instance, I have no idea what this curve is. I can still do computation and integral, right? You should still be able to do that. Here, easily I'm going from 0 to 1. I have to multiply xt with x prime times, x prime and y prime. X prime is 8, y prime is 16. I have to do an integral with respect to t. That's why I have to replace x by 8t and y by 3t squared here. Okay? So not only you have to take the derivative, but also when you plug in this vector field with respect to x, y, you have to plug in t naturally. Otherwise, there's no way you can do this integral. And you have to switch everything into t to do this single variable calculus. So this is going to be from 0 to 1. I have 8t, 3t squared. Dot product is 8, 6t dt. So in the end, I have the integral from 0 to 1, 64t plus 18t cubed. And this is a pretty easy computation, and I already have done this. It's going to be 33 divided by 2. Okay? So I'm completing this single variable integration pretty quickly because every one of you should be able to do this. One thing I do want to mention here, listen carefully. So throughout this computation, I have this parametric equation of the curve. This equation of the curve actually appears twice. One time I'm taking the derivative together on the tangent vector. So I have to use this one time right here. All right. The other time I have to plug in x, y for t here. Right? So I have used the parametric equation for the curve when I replace x, y by t. So I'm actually using this parametric equation for 2 times. Am I clear? So you need to use it 2 times. One is taking the derivative. The other one is to replace the vector field by the parametric equations. Okay? So you need to use these 2 times. And these 2 times sometimes might be confusing. So here is another example I want to draw. So this one is not that complicated. Again,